Welcome everybody to the Toon Show, MC Toon Live. Which is it? Well, it's both. This is going to be a live recording of the podcast for the Toon Show. So you get a little behind the scenes here, and you get to watch it now. And if you watch it later, bonus. And if you don't watch it later, you've already watched it. I will be. I'm on here with Cody Payne. And he's going to pop in a minute. But here's what's going to happen. I will switch modes. I'll introduce the podcast. Don't get fooled. And then I will do the podcast part. He'll do some talking, some presenting, and then I'll end the podcast. How I will end the actual podcast. Don't leave, because then we'll have some back and forth with the audience. So, Cody, if you're there, Cody was on and then he turned off his video and audio. So there we go. You got to get your audio still. It's still muted there. I can hit the ask to unmute. There we go. See if you get it there.
There we go. Can you hear me now?
There we go. Yes. All right.
Hey.
Well, welcome, Cody, and so I'll start the podcast, and then we can get to it, and then we will do the Q&A afterwards. So,
cool.
Get your questions ready for him. Welcome to the Toon Show, where we like to introduce and discuss and talk with some smart people, and I call them Smarty Pants. And today's Smarty Pants is Cody Payne, and he's a physics student at some. I'll let him introduce where he is. Cody, can you let us all know where you're studying, what you're studying?
Yeah, so I am currently based at the University of North Dakota in Grand Forks. I am studying physics as my discipline, pursuing my PhD, and specializing in quantum optics, actually. So the study of photons and all of their interactions with matter and various crystals and mirrors and all that fun stuff.
Well, that's really cool. Good stuff. And we are discussing today the scientific method. And while this podcast isn't strictly about flat earthers, but we get into it a bit because they like to taint science with their silliness. So the topic is scientific method and what flat earthers get wrong about it. So go ahead with whatever you have, and we're looking forward to it.
Okay, cool. So yeah, I will. I'll just kind of talk. I have some notes that I'm going to go off of, and whenever you want me to stop and kind of elaborate on something, or just stop to chat, just force me to stop. Right. So, as some people in the chat are kind of pointing out, of course, there's not just one scientific method. We all kind of know that. There are basic general principles of forming a hypothesis and trying to answer some particular question by making a prediction and testing that prediction. A better name for this talk might be something like what folks get wrong about the philosophy of science, which is what we'll kind of go into. So I think, how do I say this? I think that flat Earth is kind of dead out of the gate when you consider how they think about science, how they go about thinking about confirmation and experiment. And so, honestly, without even touching on scientific facts and observations and experiments in and of themselves, I think we can kind of refute flat Earth by just showing that they don't even have a leg to stand on from how they're approaching epistemology. So let's kind of get into it. And as we go forward, the way when I was writing these notes, the way it kind of evolved was I started moving away from like refuting flat Earth and more into just a general discussion of philosophy of science. So maybe we'll get there, maybe we won't. But we all kind of know some of the really basic things that FLIRFs say, kind of the unholy trinity of Nathans will say some really, really dumb things. So a couple of the really dumb things that the unholy trinity of Nathans say most often that's associated with them is, for example, if you show them an experiment, they'll immediately go, well, what's your IV? What's your DV? What's your CV? And of course, not all experiments have a well-defined independent variable and dependent variable and control variable. So that's, of course, just a really bad way to look at a scientific experiment is, well, if I can't identify an independent variable, then that experiment, just throw it out. It doesn't matter what it says, doesn't matter anything about it. Another one of my favorites is, well, you can't use any kind of man-made apparatus. You can't use a measuring apparatus. You can't use any kind of man-made technology when you're doing an experiment, unless it's a Nikon P900. Or it confirms flat Earth. Like if you want to shine a laser across the Sea of Galilee to confirm flat Earth, you can do that. That's totally fine. But if it confirms the globe, you can't use man-made apparatus. So, and then finally, a third really dumb one that kind of gets past our just ideas of things we're not even going to dignify with a long discussion. It's, well, if you're not putting your hands on your IV and manipulating it and moving it around with a screwdriver, then that's not a valid experiment. That the only way to do an experiment is to have your IV be something that you physically manipulate with your own hands. And of course, that's just not true. And it's not even worth dignifying with a response. But let's now get into a little bit more subtle ones. So the fourth thing I have listed here is, first we'll say the cause that you're trying to investigate. What you're trying to say is causing your physical phenomenon. That's one and the same with the independent variable of your experiment. That's, of course, not true. But there's some interesting subtlety there, which I would say that when you're actually doing a scientific experiment, at least in the realm of physics, the kind of cause of what you're investigating, or you might say the law of nature that you're trying to investigate, actually shows up when you do a curve fit. So if you plot your data and you fit it to a line or some other curve, the parameters of that curve fit, like the slope and the y-intercept, for example, usually encode something about the cause of the physical phenomenon you're investigating. For example, if we want to do a Cavendish experiment and investigate, well, we think gravity is causing this. A really nice way of setting up that experiment is we change the mass values. We have mass on the x-axis, and we have a measured force on the y-axis. And a really nice thing to do might be get several data points of force versus mass, plot those. What Newton's law of gravity predicts is, of course, that you will get a straight line fitted to that data, and the slope of that line will be big G over the distance between the masses squared. So that's what Newton's law of gravity predicts. So you can see that the cause, the kind of big G, is encoded in that slope parameter. I'm sorry, I lost my train of thought. And then, of course, you could do the same thing, but you could plot force versus 1 over that distance squared, and you would again get a linear graph. And that would, so if you do both of those things, you could look and say, well, look, we have this number that keeps popping up in this experiment, this constant that's just kind of in the slope parameter. It's 6.67 times 10 to the minus 11 some units. Well, that seems like it might have physical significance. And of course, it does. That is the cause we're investigating. That is Newton's law of gravity. And if we did this with a sufficiently large data set, then we could say we've truly confirmed Newton's law of gravity. And FLIRTs can't really respond to that. The best thing they could do is say, well, actually, you've done your analysis wrong. They could say, actually, maybe you should have fit that to a quadratic fit for some reason. And then that would correspond to a different law of gravity, and that would falsify Newton's law of gravity. Of course, no flare has ever done that or ever could do that. So what they resort to is the second option, the Whitsitt option, of saying, well, what we're seeing in the Cavendish experiment is just some confounding variable, like electromagnetism. So we're looking at not a correlation between the force and the mass, but we're looking at a correlation between the force and something that's correlated with the mass. But the thing that you have to kind of think about there is, if that's true, we've still confirmed mass attracts mass, because we're still observing a correlation between the force and the mass. And usually, if Whitsitt wants to say, well, it's electromagnetism, he would have to have some mechanism that puts electromagnetism in a one-to-one relationship with mass.
Yeah.
And that sort of mechanism doesn't exist. So again, this is just one of those ways that flat Earth is kind of just dead out of the gate. You can't really refute this sort of experiment, because it's fairly straightforward to see that the correlation you're investigating is really there, is really emergent from this data. So that's one thing that let's say that's thing number one that Flurfs get wrong about the way to do science is, of course, you can confirm a cause, but it's more subtle than that. And okay, so let's stop there for a second, and maybe there's questions or things to discuss.
Yeah, people may or may not know the unholy trinity of Nathans, or who Whitsitt is. It maybe bears explaining the unholy trinity of Nathans is Nathan Oakley, Nathan Roberts, and Nathan Thompson, though Roberts has been gone for a while. But of flat earthers, that especially Nathan Oakley is very good at getting science wrong. And then Whitsitt is Austin Whitsitt, another flat earther who declares that gravity doesn't exist because something electrical causes it, without actually providing any confirming evidence.
Right. So are there, is there anything you want to kind of stop there and really in touch on, or should I keep going?
Yeah, you can keep going.
Okay, cool. So I think one thing that would really behoove us to drill in here, that we don't really talk about that much, is that when we do something like the Cavendish experiment, and bear in mind I'm just using the Cavendish experiment as an example, it doesn't have to be the Cavendish experiment, it can be any experiment. But when we're doing something like the Cavendish experiment in physics, we're not just doing one observation. We're not just putting two masses together, seeing, oh, there's a force, and being like, okay, the masses cause the force, we're good to go, and calling it a day. That's not how science is done, but that's kind of how Flurfs thinks science is done. They think science begins and ends with a single observation, which is all that any flat Earth experiment is. The Sea of Galilee experiment, for example, is just a single, when it comes down to it, is just a single observation. There's no real scientific method there, but they're the ones who want to harp on the scientific method.
Yeah.
But we don't do science with a single observation. We do science with data. So that's one thing to really drill in. We do science with data, not with just one observation and just draw whatever conclusions we want from that. That's just not how it's done. And a data set gives us much more confidence in the things we're investigating than just a single observation does, of course, because that is quote unquote the scientific method. So one thing that we could kind of touch on a little bit, that kind of ties in nicely with my next point, is there's actually a little bit of subtlety with regards to, if we want to say we are investigating a cause at all in science, because of course you have, some of you might be familiar with Karl Popper, who said well, science, it doesn't concern itself with causes. Science doesn't concern itself with confirmation of any kind of mechanism, any kind of law, any kind of theory. It only concerns itself with falsification of those theories. So this is something. This is a big can of worms, of course. That, but flat earthers don't get into the can of worms, of course. I learned this term recently from Craig's channel, or from his debunks of the flat earther who claims not to be a flat earther, Mind Shock. Mind Shock keeps bringing up this thing called the false cause fallacy, which means essentially what I was talking about. If you do a Cavendish experiment and you just do one observation and you say, okay, the cause is mass attracting mass. Well, of course, that's a fallacy. And Popper would go deeper into that can of worms and say, of course, you can't establish cause. You can't establish an explanation. All you can do is falsify. All you can do is say something is wrong. You can never say something is correct. And that whole can of worms has a nice little name on it. It's called in philosophy of science, it's called the problem of induction. So, and it's related to the relationship between a deductively valid structure that we call modus tollens, which says if you have well, I'll state it. It says if P, then Q, and then you have Q, or I'm sorry, then you have not Q, you can then conclude not P. So that is like scientific falsification. If hypothesis, then observation, not observation, therefore not hypothesis. And that is deductively valid.
Yeah.
But if we want to say we can confirm something scientifically, that is kind of like affirming the consequent, which is deductively invalid. And affirming the consequent is the logical form, if P, then Q, Q, therefore P, which is not valid. And it seems like, well, according to Popper, that's all scientific confirmation can aspire to. All scientific confirmation can aspire to is if hypothesis, then observation, observation, then hypothesis, but that's invalid. You can't draw conclusions from that. That is the problem of induction. So one resolution that I like is the use of something called Bayes' theorem, which is related to probability calculus. And Bayes' theorem, in brief, says that we can assess the probability of our hypothesis being true given some observation we've made by mathematically equating that to something else. And something else is the probability that the observation will occur given the hypothesis is true, multiplied by the probability of the hypothesis by itself, divided by the probability of the observation by itself. So Bayes' theorem says P of A given B equals P of B given A times P of A over P of B. Some of you might be familiar with that. All it is a way of relating probabilities given two kind of data sets, if you will, or two ideas.
It outputs a number of likeliness.
Yes,
that
exactly.
Something is correct, yeah.
So if we kind of apply that to the idea of scientific confirmation, then it suggests that we can come close to confirming our hypothesis with the observation we've made if the what we call the prior probability, that P of O independently of H, is very low, but the probability of the observation given the hypothesis is true is quite high. So what that would be like is if we have some observation that's by itself quite unlikely, but under certain circumstances, under this hypothesis, it becomes demanded. This hypothesis actually demands that this observation take place. That's kind of gets into, if you've read Popper, what he talks about the the aspect of risk or the aspect of the danger to the hypothesis. The hypothesis has to strongly demand that the observation take place. And if it does, while the observation itself is quite unlikely by in and of itself, then by observing that, we come close to confirming it. We bring probability of hypothesis given observation somewhere close to 100%. Does that make sense? I want to.
Yeah, it does, and the of course the probability never reaches 100%.
Right, of course.
Right, it approaches it, and as it gets closer and closer, you're more certain of it. Right.
Right, of course. Yeah. Yes. And the interesting thing is, and I've not read this anywhere, but to me, it seems like this encodes Occam's razor. Like we get Occam's razor out of this for free, because if
state Occam's razor for.
Oh, Occam's razor says that the hypothesis containing fewer assumptions, fewer elements, or the word that I like to use is ad hoc, fewer ad hoc elements to the hypothesis. That hypothesis is more likely to be true over the hypothesis that contains more of those ad hoc elements. So this basis account of confirmation and induction kind of encodes Occam's razor, because a P of observation given hypothesis is kind of weak. The hypothesis doesn't really demand the observation. You have to plug in a lot of other things to get the hypothesis to predict this observation. Then that brings P of observation given hypothesis down, which in turn brings P of hypothesis given observation down. So that's a cool thing that kind of drops out of this account of scientific confirmation. And of course, it also encodes, on the exact other hand, it encodes why predictions are so powerful, why in science. Because a prediction is nothing more than saying P of observation given hypothesis is quite high. The hypothesis, like I said, very strongly demands that this observation takes place. It predicts this observation. It makes this observation absolutely essential for the hypothesis to be true. And so, again, that comes back to the hypothesis has to be at risk. It has to be in danger of falsification in order to be confirmed. Except Popper doesn't take that next step. He just says the hypothesis needs to be in danger.
He stops. Yeah.
But what the hell, like, do we care? Because we're not confirming the hypothesis anyway. We're just saying
that's what he's that's his
position. Yeah, exactly.
So, like, Popper really did appreciate Einstein's prediction of the 1919 eclipse because it was very bold and definitive. If it matched, it meant this, and if it more so because it's Popper, if it didn't match, it meant it was wrong. So it was very bold.
Right. Yeah, very much so. So that brings us to kind of my next point, which is the value of predictive power and explanatory power in and of itself. And also the idea of the self-consistency of a hypothesis or a theory. One thing, again, this is a thing where the flat earth position is just dead out of the gate, because flat earthers cannot bring an argument that validly represents a globe prediction and then refutes that prediction. They cannot bring a valid modus tollens argument of if globe, then X, not globe. And so if you can't do that, if you can't meet the globe theory on its own terms and find a prediction, make a correct prediction about the globe, and then falsify that prediction, you're dead out of the gate. You're not doing science.
Yeah.
And if the globe can survive every prediction, if it can survive every attempt at falsification and still be internally consistent and non-ad hoc, honestly, you could call that in and of itself an account of scientific truth. And that's something we can kind of get into a little bit later. Is that would be kind of like a scientific anti-realist view that science is really just about making good predictions about what we'll observe. It really doesn't concern itself with what actually exists in reality. And there are actual philosophers who hold this position. And I'm not advocating this position, I'm actually the opposite. But my point is, there's a valid case to be made that science only concerns itself with consistency. It only cares that the hypothesis has predictive power, has explanatory power, and is self-consistent. And that is the true hypothesis by scientific standards. I think we can go farther than that in investigating truth and reality and what is actually out there using science. But honestly, if Flat Earth cannot even get past this simple hurdle of showing some internal inconsistency, of showing some valid argument against the globe, like some valid deductive falsification of the globe, it's dead out of the gate. There's no reason to even take it seriously. So honestly, like I was saying, independent of the scientific confirmations, like the positive confirmations of the globe, independently of that, we don't even need to bother with refuting Flat Earth if they can't even meet this basic hurdle.
Yeah.
So that's something really kind of interesting and really, really damning for Flat Earth, I would say.
Yeah, and it's important to know why they don't ever actually do to understand why they don't ever actually do a real falsification test of the globe, is because they have incorrect application of the hypothesis.
Right. Exactly. Very much so. And honestly, that would be a challenge. Like I challenge flat earthers in these Facebook groups all the time. Can you give me a valid prediction of the globe?
Yeah.
And they can't.
They always get it. They get it all wrong.
Yeah. The closest I've seen, maybe we can discuss this for just a second. The absolute closest thing I've seen is actually a deductively sound argument. Deductively valid argument from Mitchell from Australia. If you remember, about year and a half ago, there was a little beef between Mitchell from Australia and Blue Marble Science, where Mitchell from Australia had gone into this museum that housed a Foucault pendulum, and there was a sign that said something to the effect of, this Foucault pendulum is not working the way it's expected to, is down for maintenance. And he made a video on that where he actually made a deductively valid modus tollens argument. If spinning globe model, then all Foucault pendulums have to meet this prediction.
They have to process. Yeah.
Yeah. This Foucault pendulum does not process. Therefore, the spinning globe model can be correct. And that's at least an admirable attempt at some falsification of the globe model. Now, of course, there are so many confounding variables with the Foucault pendulum that could be causing it. It has to be set up very carefully. It has to be set up very precisely to actually work properly. So, of course, it's not a deductively sound argument, which means it has true premises, but it is deductively valid in the sense of if its premises were true, its conclusion would be true. Do you have any thoughts on that?
It illustrates that they're not looking to build a valid deductive test. They're looking to build a deductive test that will get the output they want.
Yeah.
And to hell with thinking about whether or not they've included confounding variable in the test. So
yes, absolutely.
So they always construct these things like that when they're talking about bottom up obstruction. They use the wrong formula, for as an example. So
So, and that brings us to another point, which, apart from that, what is the best flat Earth argument? Kind of by these standards of philosophy of science that we've been going over, by what some respectable philosophers of science might take and say, what would be the best flat Earth argument? And the one I would vote for is really not a flat Earth argument at all. It's an argument against gravity. And it is, gravity is a false theory. It's a falsified theory because we, Vera Rubin, observed galaxies that do not meet the Newtonian prediction of gravity, and from whence comes dark matter. And of course, dark energy is not the same thing, but it has slightly related observations that we need dark energy. So because we need dark energy and dark matter to make the predictions of Newtonian and Einsteinian gravity match reality, then gravity can't exist. And this does get a little bit into the philosophy of science weeds. Again, we'll come back to Popper. Popper did discuss this problem. He said, when can you truly say a hypothesis is falsified? And because technically you can always add something to the hypothesis. You can always just take a part of the hypothesis away and kind of cheat. And if you cheat enough, you start to diminish the utility and respectability of science. And this is Popper saying this. So the question is, when are we allowed to make these additions and subtractions without throwing out the whole theory? And that's a topic of discussion in and of itself. I don't think it's a settled idea in philosophy of science by any means, but when it comes to dark matter and dark energy, I do think we have an answer, and it's that, of course, we weigh the added ad hocness of dark matter and dark energy against the loss of explanatory power and predictive power of general relativity and Newtonian gravity. And if the scales tip in balance of keeping gravity, then we keep gravity, even with this new addition to the theory. So, is that something you have any thoughts about? Let's stop there for a second.
Yeah, those are then, they're somewhat subjective,
right?
Or putting value on it, you might say, is inductive, which is the thing that Popper always was trying to avoid.
Right.
And of course, that's one of the, if you just keep going to all the way down the line with Popper, you'll wind up in a point where you're using induction. So it gets then, and the whole point is to not use induction. So it gets self-defeating a little bit if you go all the way with to the end of the line with it.
Yes, it certainly does. Yeah, definitely. I'm sorry. I feel like I'm not having a good kind of back and forth with you.
I
don't mean to.
I'm trying to not interrupt you.
No, I appreciate it.
Let you present. So,
but I don't want it to be hand wavy when you say something.
Yeah. So the and I this version of it here, or this take on it, where you have the Bayes formula and things like that. It's a good answer because when you read Popper, you get to the end and you're like, well, okay, I'm unsatisfied.
Yeah.
Because you're like, oh, we'll do a falsification test. All right, we didn't falsify. Do it again, didn't falsify. You do it 100 times, you didn't falsify. You do it 1,000 times, you didn't falsify. Well, when are you done? You're never done. If you're pure in Popper's version of it. And eventually, and this was the unsatisfying, where you get to the end, you're like, okay, fine. We're not going to do another falsification test. We're good. But that doesn't, you don't get a stamp on it as done.
Yeah.
It's just, you walked away because we can't do it again. So
yeah, exactly. And to me, that's a very weak view of science. Like
yes.
There's some utility, there's some value in failing to falsify. Just as much as there is in succeeding to falsify.
Yeah.
So yeah, Popper is definitely I think we agree. Popper is definitely incorrect on this account.
Yeah. But
Um,
it's pretty. Yeah, I don't think there's a whole lot of people that are like, yeah, all the way with Popper.
yeah,
But yeah, because you get to where you actually have to do some work in the end and say, well, we need to actually use what we figured out before to do new stuff in the future. And so we'll take the 10, 100,000 times that we confirmed it and take it to say, all right, or sorry, not confirmed, failed to falsify in Popper's
yeah,
version, and say, okay, that's good enough for us. We need to be pragmatic and we're going to move forward. And so that's where you get into things like Thomas Kuhn, who said,
mm-hmm.
this is how people actually just do science, right?
Right.
You try to do the falsification stuff and you kind of work around the fringes of that. And once you've shaken it out a bit, you say, all right, what? That's pretty good. We have a really good understanding of it. We're going to move on and now solve some problems.
Right, and that's Kuhn's idea of normal science. But the whole idea of paradigm shifts, that kind of comes back to what we were talking about with when do you throw a theory out?
Yeah.
And I can't remember what Kuhn's conclusion on that matter is, but that's kind of his entire idea. Is at some point that balance shifts, and that's when the paradigm shift happens. I don't know if he gave a rigorous account of when that happens.
No,
but.
well, that Kuhn wasn't about rigor. So his description of when a paradigm shift is going to maybe happen is when you start to find holes in the current paradigm. Things, as you start moving forward and using that science, you find that this doesn't work and this doesn't work. A bunch of other things still work, but oh, we ran into another thing that doesn't work. Mm-hmm. And you accumulate these problems, and then people start to get, maybe there's something we don't understand, and then they start directly testing against those and providing hypotheses to push past that. And then either, from Kuhn, you either get a revolution, or mm-hmm. those things wind up just getting to, oh, well, we didn't understand these holes that we thought we had. We didn't have the right understanding, so you don't get that revolution because you did, in fact, have a good understanding. You were correct, but some of the tests you were doing were just not good enough or not well understood. So,
right.
So
I can't Einstein, think of. I'm trying to think of an example where that latter case happened, where the crisis is resolved within the current paradigm. In physics, I can't think of an example off the top of my head. Maybe
there probably are, but because nothing happened, it's not documented as
right.
A crisis almost happened, but nobody, people, it's science is littered with people that did tests about things that they had previously done tests on and didn't quite understand.
Right.
And so that's where we might see those, but you'd have to examine the details more closely. But the crisis example, one of the classics, of course, is Einstein, and that there was previous to Einstein, there was this idea of the luminiferous ether was the transport for light, and there were a couple holes that were showing up, and things weren't working. They weren't able to make some predictions about some things, and that matched observations. Then Einstein came along and said, "Here's a different explanation for it." It came in and it answered the questions that the holes were showing before.
Right, of course. Yeah, that's a good point. That's a very good example, and almost like the quintessential example of this.
Yeah, another so that we don't, Einstein gets a lot of attention on it. There's others though. So another would be the Bohr model of the atom. So before Bohr, they didn't have a really good idea of the atom. Bohr came along and said, well, it's we've got the nucleus, and then we've got the electrons, which are individual balls as well, and they're going around in circles around it.
Yeah.
And Bohr introduced that, and it was, I don't remember even what the idea was before. And that was
the plum pudding model.
Plum pudding. So yeah, the electrons were in a pudding around it. Yeah. And Bohr's model was like overnight success, but it was only lasted, 11 years before the next one came along because some holes were showing up in it.
Right.
I don't remember the exact number. I think Kuhn talks about it.
Mm-hmm.
So.
Yeah, so I think Bohr's model would have been like 1915-ish, and
Yeah,
then
early.
quantum mechanics was completed in 1927, so about 11, 12 years.
Yeah,
Yeah,
there you go.
exactly. Yeah, cool. So let's get into let's stop talking about flat earthers for a second and move into a kind of really cool topic. So let's move away from the epistemology of science and into the metaphysics of science.
Mhm.
Let's talk about scientific realism versus scientific anti-realism. Um, so the question of realism versus anti-realism in science is, of course, as I kind of talked about, are the entities that we talk about in science, especially those that we can only indirectly observe, for example, space-time or quarks or electrons even,
Yeah.
or the wave function, what have you. Are those entities real? Do they actually exist in reality? Or are they just equations that are convenient to plug some numbers into on a computer, and black box does some stuff and it spits out what you should see in an experiment, and then on and on and on, all we do is just try to find better and better and better toy models, so that all we really do is we just make science incrementally more uh, correct, or not correct in a truth sense, but correct in a predictive power sense.
Yeah. But it's kind
Uh,
of abstract.
right. Yes. Yeah. Those entities are very abstract. So that is the question. Does the wave function exist? Is a popular one, of course.
It's a function.
Uh,
No.
but but of course it describes something.
Yes.
It's like the word chair and the relation of the word chair to the actual chair in my
Yeah.
office. The wave function refers to something in reality. At least that's my position. There is a respectable counter argument to be made, of course. Uh, so, but my kind of take on this is, when I talk about the chair that I'm sitting in, I don't adopt this super high view of truth and reality and existence of, I could never be wrong. I couldn't be a brain in a vat. I couldn't be hallucinating. I couldn't be asleep in a coma. Whatever. I don't adopt this super high view that everything I see is a one-to-one match with reality, but I adopt a functional kind of definition of truth, where I say, if I can see it, if I can smell it, if I can touch it and sit in it, and I all I'm really doing in the kind of anti-realist sense is making predictions about what will happen if I measure the chair in certain ways. But that doesn't detract from the reality of the chair. It's not mutually exclusive that the chair that exists in my mental representations that inform what's going to happen if I try to sit down here is not mutually exclusive with the idea that there's something actually here. There, it might not be a one-to-one match with my mental representation. Of course, it's not, but it's actually here. And in the same sense, a quirk is actually there because it informs our predictions accurately. It is a qualitative as well as a quantitative idea that informs our predictions. And just in the same way that the chair is real because it, and by that definition of real, it just informs my predictions, the quirk is real because it informs my predictions. Um, and I'm sure almost everyone has seen The Matrix. There's a line in that movie that I kind of am hearkening to, where Morpheus says, what is real? How do you define real? If you're talking about what you can see, what you can touch, what you can taste and see, and smell, whatever, then real is just electrical signals interpreted by your brain. But
Yeah.
why is that electrical signal in my brain being interpreted? It's going through computations. Why doesn't that detract from reality? But the measurements taken at a particle collider, those are just abstract. Those are just, they don't really have a concrete underlying reality, because they're being filtered through a computer. They're just a result of a bunch of noise that the computer somehow makes sense of, but that's not functionally or qualitatively different than what's actually happening in my brain. Um, so I kind of take that view of scientific realism. Do you have any thoughts before I continue with that?
Um, yeah, it's an interesting way to come about it, because then it does do brain in a vat, or um, specifically brain in a vat, but also, butterfly having a dream or whatever. Yeah, I definitely lean towards, well, if I can experience it, then that's real. So
Right.
yeah.
But would you say like the example I keep coming back to is quarks. We don't have to stick on quarks, but would you say quarks are real by that same standard, that you can experience it and it's not inherently like less direct than your experience of anything that you feel?
I think it's less direct, because I can't experience a quark by picking it up. It
Right.
has to be done through an instrument, and those instruments are several layers away from picking it up. So I can pick up a piece of wood, um, and through, you know some layers of abstraction and instruments, I could, I can't pick up a cup of lava, right? I'd
Well,
have to
yeah.
use an instrument to pick that up. So I'm
Right.
removed from it because of that instrument. Well, a quark is many layers
So,
beyond that.
right. It is. I don't know if that's and this is a fine point to just agree to disagree, but I don't know if that's a salient uh, distinction. I don't know if the number of layers of separation is necessarily has any bearing on our assessments of reality
Yeah,
or
yeah.
not. And it's really like phenomenologically, how do you define a layer? Because there's multiple layers of my cognitive processing for
Yeah.
everything I feel as well, right? Um, but yeah, I see where you're coming from, and of course that's a reasonable view to take. That yeah, like I've never been to a particle collider. Of course I can't experience a quark just in the same way I experience. So I have to take their existence with some grain of salt. I'm not denying that,
Yeah.
but I think there comes a point where the scale tips in favor of saying, yeah, it's probably real, um, by the same criteria of reality that we use in everything.
Yeah. You can do things with it. So an electron's maybe better than a quark,
Right.
because we all use computers, and computers wouldn't work if we didn't have a really good understanding of how electrons work in semiconductors.
Right.
Right? We don't build computers out of quarks, but we build them out of things that use
I mean,
electrons.
technically we do. There's two up quarks and a down quark for every atom and
Yeah.
every proton. Um, so where am I in my notes? Oh, this brings us to it back to the kind of Bayesian account of confirmation a little bit. That one thing I see anti-realists say in response to this kind of account of like this optimistic view of confirmation and this optimistic view of realism is, well, there's technically infinitely many hypotheses that you could create that would make these same predictions. So we can't do anything confirmatory exactly because any hypothesis we have said that we have confirmed is just one of infinitely many possible hypotheses which would make the exact same prediction, but are all physically qualitatively different. And there are hypotheses like that. A lot of them pop up in something we might get to in a little bit, which is like the interpretations of quantum mechanics. For example, the so-called pilot wave hypothesis or interpretation makes, but by design, the exact same predictions as just standard quantum mechanics. And so how can I say one is correct when they make the exact same predictions? But in most cases, for example, general relativity is a better example. If there's infinitely many hypotheses that are qualitatively different, but quantitatively the same or better than general relativity, where are they? Name one. Give me one. Because physicists have been trying to do that for 100 years, and so far they failed. It doesn't mean they won't succeed one day, but I don't think that detracts from the truth of general relativity now. I think general relativity will be a special case of this new
and that's
theory.
what we've found is that when a lot of the time when there's that scientific revolution, the understanding is an enhancement of the previous, not a destruction of the previous.
Right. Exactly. So yeah, to these kind of detractors who say, well, we're not really confirming because there's infinitely many hypotheses, my response is name one. And I don't think you can. Especially not one that's not ad hoc, that's not designed from the ground up with all the predictions built in, which would, of course, from a Bayesian account, be confirmed much more weakly than general relativity. And kind of this runs into the problem of appealing against miracles. And there's a lot of ways I could go into that I don't want to. But what I'm meaning right now is if GR were wrong, qualitatively wrong, and it makes these predictions as good as it does, that would be a miracle. It's less of a miracle that GR is qualitatively correct as well as being quantitatively correct, especially when we consider from a historical perspective that Einstein designed general relativity from qualitative considerations, from considerations about, what is the simplest way of looking at this? So, the universe should be simple. The universe should be beautiful. That was kind of Einstein's conviction. And Dirac also said something to that effect. That's a strong conviction among physicists that when I'm designing a theory qualitatively, it should be beautiful.
It's a bit like Occam's razor, but
exactly.
It's purely subjective. Right?
Right.
Well, let's go with the hypothesis that looks the best, that gives me the most satisfaction for being awesome. That's not necessarily the right way, but there's a lot of cases where we found that to be correct.
Right. And of course, Sabina Hassenfelter has a whole book about that we shouldn't, that shouldn't be a criteria.
I got it on the shelf right there. Haven't read it yet.
Oh, nice. But I think I've read it. Well, I've listened to it.
Yeah.
So one view, let's get back to realism for a second. And let's talk about what's currently kind of in vogue among scientists and a lot of philosophers of science. Although I believe philosophers of science tend to lean towards anti-realism, whereas actual scientists tend to lean towards realism. Don't check me on that, I might be wrong. But that's kind of the way I understand the debate. But there's a subfield of realism called structural realism, which is subdivided into what's called ontological structural realism, or epistemological structural realism. I don't know much about epistemic structural realism, so I'm not going to dive into that too much. But ontic structural realism effectively says, if I replace the entities in my theory, if I replace force and energy and action and quarks and what have you with things entirely different, I can still build successful theories. But what would still be maintained is the connections and the structures I found and the laws governing the structures that I found between these entities. So that's a very kind of appealing view, and I think that has some amount of truth to it. It's something I've been meaning to read a little bit more deeply into, because what I gave right just now might be a very, very dumbed down version. Almost certainly it is a very, very dumbed down version. But unfortunately, there's not a lot of good books on the topic or anything, so it's hard to find. But one kind of convenient thing about ontic structural realism is it resolves the frequent flat earther thing about, well, gravity isn't a force. You can't use Newtonian gravity because gravity isn't a force. Not that really needs resolving.
Yeah.
But it says it allows Newtonian gravity to still be true and Einsteinian gravity to still be true, but it just replaces force, the entity in Newtonian gravity, with a new entity, a new kind of way of piecing together the universe in Einsteinian gravity. But they can both be true. They just reduce to the same structures. And that's like kind of appealing.
And you know, there's the nuance of the when you resolve Einstein's equations and you get Newton's equations, you wind up with the same equations, but when you're in Einstein's, the mass has a different meaning than mass in Newtonian. You wind up with the same equation, you wind up with the same m there,
Mm-hmm.
but there's this different meaning there. You know, the meaning behind it doesn't matter when you're doing an experiment or when you're measuring the mass.
Right.
So the output
Exactly.
is the same. But
exactly.
Yeah.
Yep. But my preferred view of scientific realism is something that's fairly new. And it's a view of scientific realism that kind of reduces to, I'm going to coin a term here, to what's called modal realism, M-O-D-A-L. And that relates to the field of philosophy and formal logic called modal logic. And in simple terms, what modal logic is it's the formal logic concerned with relationships between what is possible, what is necessary, what might happen, what might have happened but didn't, which is called counterfactuals, things like that. So counterfactual truths is one of the more important things. And that brings me to, I kind of had this kind of realization fairly recently, again, listening to the Mind Shock rebuttal from Craig, which is in the whole thing they go into, if anyone's watched the video, there's this whole thing that Mind Shock makes a big deal about, where Craig is asked, define energy. I was like, okay, how would I have answered that question? Yeah. But energy, of course, is defined as the capacity to do work. But that is a modal fact. That is a counterfactual truth. It says if I tried to do work, if I tried to have this system A do work on system B, the amount of work that system A could do on system B is defined as the amount of energy in system A. But that is a counterfactual truth. That doesn't necessarily obtain. So that's a really appealing to me view of scientific realism, that scientific realism reduces to these counterfactual truths having reality. They're objectively true, independent of us thinking about them or measuring them, whatever. These counterfactual truths have objective reality in and of themselves. And this is actually, this is not just me, a book very recently was published called The Science of Can and Can't. I have it on audiobook where I would show it, by a physicist named Chiara Marletto, works in quantum information science, quantum computing. And this is kind of her account of science, scientific realism, scientific laws, is that science and scientific laws and scientific entities are really reducible to these counterfactual truths, which is a very, very interesting and very appealing idea to me. And actually, it's been defended elsewhere by a philosopher who's based at the University of North Carolina named Mark Lange. And he has a book called Laws and Lawmakers, which tries to give an account of what is a law of nature. What do we mean when we talk about a law of nature? And the idea that he puts forward is a law of nature is, again, a counterfactual truth or a modal truth about, for example, the law of gravity says, if I have mass A here and if I have mass B here and there's some distance between them, there will be a force between them of some magnitude. Even if those masses never get near each other, that counterfactual truth is true of every pair of masses. That's a really, really appealing view of science and laws of nature to me. So I'll let you have the floor and give thoughts about it.
I don't know if I have a whole lot to come back on that. I don't see. I guess I didn't see that as just because there's two masses and there's a force, even if they don't get close to each other. I didn't find that appealing. I don't know what I missed that you thought was novel.
Well, I guess it's the question of, well, if I asked you flat out, what is a law of nature?
Oh,
like metaphysically or like ontologically, what actually is a law of nature?
Yeah. Something that, without looking it up, something in nature, a phenomenon that it can be described. Yeah.
So my problem with that is, so that's what a lot of people say, and a lot of scientists say, is that a law of nature is kind of a description of, we observe these regularities and we state that this regularity usually occurs in nature when we observe things under this set of circumstances. And by definition, that's a law of nature. The problem is, I agree that's a law of physics, but I think there's a distinction between what you would call a law of physics and a law of nature. The law of nature is what I believe underpins the law of physics. And I believe the law of nature itself needs to have some reality. It needs to be more than just a human description, because its role, the reason it exists, the reason we say it exists, is to explain things. So, for example, if I asked you the question, why did we not accelerate at 9 times the speed of light into the sun just now? Or just now? Or just now? Or just now? Or just now? That has an explanation.
Yeah.
And that explanation is a law of nature. A law of nature forbids that from happening. But what is a law of nature that has the power to govern and forbid? It can't be just a description, because then you're reduced to describing things in terms of the descriptions. The things have regularities. Because of laws of nature, because of regularities,
and we've just described them. We've discovered them and then produced a description of it, typically with math, to bound the relationships.
Mm-hmm.
Yeah.
Right. Yeah. So you would agree there's some objective relationship there.
Yeah. There's something keeping us away from going into the sun. There's something preventing from going the particular velocity you mentioned.
Mm-hmm.
And those are in nature, and even if we had never discovered them or understood them, they'd still be there.
Right.
So there's potentially any number of aspects to nature that we have yet to uncover and describe.
Right. Yeah, we agree on that. I absolutely agree on that. Yeah. But and I don't know. So I believe there are laws of nature. I don't know if we've discovered any law of nature. Like, we've discovered a lot of laws of physics. I don't know if we've discovered any truly fundamental law of nature. Something that comes close would be like Hamilton's principle, which you might know as the principle of least action. Things travel along the path that minimizes the difference in potential and kinetic energy. Are you familiar with that? So
not super close.
So that might be a candidate for a true law of nature. It seems to be completely fundamental. Maybe, well, actually it's not, because it can actually be derived from quantum mechanics, interestingly enough. But yeah, so that's kind of my take on laws of nature. Is I believe this account, in terms of counterfactual truths, is really satisfactory, is the word I'll use, account of what these like fundamental underlying laws of nature actually are. And I believe it dovetails really nicely with quantum mechanics. Quantum mechanics, the plain sense of quantum theory is that it's about these counterfactual truths. It's about what is possible. If it is possible that the photon goes through the left slit or the right slit, that has a different implication, that has a different experimental outcome than if you measure it and you know it actually just went through the left slit. It's that possibility. It's the in terms of what is possible, that actually impacts the world. And so we have some link through quantum mechanics from these kind of abstract counterfactual modal truths to actual experimental outcomes. And it seems like if the universe is if it turns out quantum theory is the more correct thing, so general relativity is subsumed into quantum theory as opposed to vice versa, which is kind of an open debate. But it seems like if general relativity is subsumed in quantum theory, then we'll have this really nice account of quantum theory links counterfactual truths to experimental outcomes. And that in and of itself gives us an account of why things are regular, why laws of nature are the way they are, which is a really interesting connection that I want to kind of explore more.
Okay.
Sorry, I'm not trying to put you on the spot. Here, let me close the door behind you really quick.
Yeah, okay. Yeah, I'm gonna have to. It's a bit fuzzy for me, so we'll wait for him to get back. Yeah, this is Cody Payne. He is a student at university here. So some people have recently come into the live chat, so you know who he is. And we're getting to he sent me his notes. We're getting toward the end of it, and then we will do I got a couple questions. If you have other questions, you can tag me, and I'm tracking them as you tag me.
All right, I'm back, by the way.
All right, hand me the lead in to that question again.
Okay, so I don't know if it was a question, but I said
prompt.
Basically, we can quantum mechanics provides some mechanism, some measured true connection between possibility, modal truths, and experimental outcomes. It seems like this is also the best account of what a law of nature is, why things are regular, why things behave the way they do. So it seems like if we get a theory of everything, there will be this connection between fundamental laws of nature being explained in terms of these counterfactual truths. It seems like there's a connection there to me. Maybe I'm wrong.
Okay.
But that's kind of my view of philosophy of science at the moment.
Yeah, I the theory of everything, it's going to need to bring in those things.
Right.
The theories provide the why, the causality between things, and so if you have the big theory of everything, it's going to have to provide the big why for everything.
Right, definitely. And I guess the question is, will that be sufficient? Will we actually explain? I guess what it comes down to is if we truly can explain everything, quantum theory and laws of nature, in terms of counterfactual truths, which is a big if, of course. But it seems like a plausible connection to me. I'm just kind of throwing that out there as a philosophical idea. It has no scientific backing at the moment, except for, I guess, through quantum theory. But if we explain everything in terms of these modal truths, will we have explained the modal truths themselves? Why are they true? What makes them true? What grounds them? And I'll just give kind of lip service to this, and we don't have to get into it. But as a Christian, I actually believe that is something that very strongly points to the existence of God, is if we need a grounding of modal truths, of counterfactual truths to explain experimental outcomes, the best account of that grounding. Why are these true? Like, what's making them true? It seems like there's some, kind of computation going on behind the scenes of the universe to determine these modal truths. Kind of where is that computation? What's happening? And it seems like that's a very strong, compelling argument for the existence of God to me. But we don't have to get into that.
Yeah. Yeah. It bridges into the metaphysical of and maybe that is the why the theory of everything has eluded.
Right.
Is that it's not a physical thing.
Mm-hmm. And of course, I will recommend anyone who's kind of interested in learning more about this, look into, as I said, physicist Chiara Marletto, who's kind of defended this idea about physics in terms of counterfactual truths. I think someone linked the book in the chat. Look up Mark Lange, Lange. His first name is actually spelled with a C, M-A-R-C. Mark Lange has some really good books on philosophy of science in general. And also look up Alexander Pruss, that's P-R-U-S-S, who has a really good book that I've read called Actuality, Possibility, and Worlds, that it kind of looks at these accounts of grounding of laws, of not laws of nature, of like modal truths, counterfactual truths, which is a really good book. And that is actually kind of the end of my presentation.
Okay, it's an interesting. I don't know. I had not heard that before. You get down to this foundational part, and then the binding together exits physical somehow.
Right.
Yeah, that's why it's resistant. I don't know. That's an interesting idea. Yeah.
And of course, anyone who wants to can reach out to me on Facebook. Just my name, Cody Payne, on Facebook, or I guess that's the only place to reach me right now. But
all right,
I would like to start a YouTube channel pretty soon.
Might it be called Cody Payne? Might it be called something else? We shall see. All right. Well, I'm gonna wrap this the podcast here. So Cody Payne, I'll put, if you're interested, I'll put in the description on the YouTube podcast to your Facebook page.
Yep, definitely do that.
And so if you have questions in the podcast on YouTube, you can find it there on YouTube if you search for the Toon Show, and that's how you can find it. Thank you very much, everybody, for joining in the podcast, and we'll see you next time.
Cool.
All right, but we're not leaving. We're not done with the interaction. That's where I will end the podcast when I upload it. So I've got a couple questions that people have sent, and if anybody has others, you can tag me, and I'll ask them. So Desert File has asked, do you know about the paper on the origin of inertia by D.W. Sciamma?
No, I've not read that paper. It sounds interesting. If you wanted to link it to me, I will definitely look up.
I will send this to you in Facebook Messenger. And then we've got from Brenda Creates, says, ask him about Lakatos and if he thinks general relativity is a degenerate research program.
Oh. Lakatos? Do you have any lead on that?
Lakatos.
Lakatos. Let me look that up really quick.
Oh, and Sleevewells says that Sciamma is pronounced Shama. Sharma?
I'm sorry. What? I'm sorry. Repeat that. I was reading.
Sleevewells, or Clivewells, as some people call him, says that Sciamma is pronounced. Hold on.
Sciamma. Did I say that?
Sharma. No, this was the question from. Oh no, where was that? Oh, the author from Desert File. It's the book Origins.
Oh, okay.
On the Origin of Inertia by D.W. Sharma.
People are giving me reading assignments. Lakatos apparently refers to a philosopher of science. And unfortunately, I don't have time to, of course, read the Wikipedia article.
Yeah, you have to read
depth right now.
everything that person wrote ever and respond to it immediately.
Yeah. If anyone wants to come on, Desert File, Brenda, whoever wants to come on, kind of go into detail about this, I'm happy to have discussion. But
yeah, let me know. Send me DM Desert File. You were on my Discord server, so you could send me a link there, or a DM there.
And then Brenda also said, is general relativity a degenerate research topic? I don't know if that means degenerate in the colloquial sense or somehow degenerate in the physics sense. In any case, I don't really see what that could mean unless she wants to elaborate.
Yeah. All right. Looking for any other. PJCnet messaged me on Discord saying that he got blocked. So I'm gonna unblock him. Hopefully it was an accident. Here you go. Because I don't mind PJCnet at all. I think he's fine. So
in general, I think you're right.
Yeah. Let's see. Well, I'm not finding PJCnet blocked on the block list, so. Yeah, sorry, PJCnet. I don't see you blocked, so. But I'll check again later. Send me your YouTube name correctly spelled, I guess. C.V. McCullough says the theory of everything is 42. The question is what we need to find. Can he explain the question? I like his thought process. We need inquisitive.
Well, thank you. Can I explain the theory of everything question? No, I don't even dive into really theory of everything topics. My only kind of statement on the topic is if the theory of everything happens to kind of subsume general relativity into more or less into our current understanding of quantum theory, that will kind of support my hypothesis about counterfactuals having some fundamental underlying role in reality.
Right. That's the questions I have from the audience.
Okay.
I haven't. So.
Is it okay if I read some comments?
Yeah, of course. Yeah. Hopefully they're hard questions for yourself.
Well, I'm not seeing a lot of questions yet.
See if you can stump yourself.
Blackburn Big Dragon says instead of God of the gaps, I would lean more towards there's something not right about our observations of extreme distances, and that's kind of a response that you always get in these kind of discussions is kind of a God of the gaps. I don't think what I claimed would be classified as a God of the gaps. I believe there are certain kind of properties of the way these counterfactuals and the way these modal truths kind of interact with reality and the way they need to be grounded. For example, I would say they have a property that you would call like colloquially it's called aboutness. In cognitive science, it's called intentionality. Counterfactual truths kind of have that property of intentionality. They're about the things they refer to. And that's a property of a mind. So I don't really feel like that's a God of the gaps. I feel like that is just kind of following the evidence with this particular argument. There are definitely God of the gaps arguments, but I don't think this is one. Am I seeing anything else?
Emerson Biggin says only about 3 of us here are qualified to ask a question.
I would love to know, like one of the people way above me, like a PhD Tony or someone.
Sleeve Wells. Sleeve Wells is.
Oh yeah, Clive Wells.
Clive. The silly pronunciation of Clive. Mallory pronounces it sleeve.
Wait, oh, okay, that's where you're getting that. When's the last time Mallory's been around?
It was a couple weeks ago.
Oh yeah, during the New Year's Eve live stream, right?
Yep.
I didn't actually watch that one.
It was the 12-hour marathon. She came on for 2 hours.
Yeah.
Of it. Mallory's Wisdom, it's called.
Yeah. I didn't watch that one.
But
I'm one of those who doesn't really like the Mallory side of things.
Oh.
I don't really find amusement in.
It is super polarizing. Every time she's on, there's a whole bunch of comments, people saying how much they like it, and then a few people, because they didn't watch it generally, a few people are like, I can't take it at all.
Although I do have a really good globe earth argument that doesn't really get brought up too much.
Okay.
The Beatles, they wrote a song, While My Guitar Gently Weeps, that says, I look at the world and I notice it's turning. So they're part of the Illuminati, so the earth is turning.
Truth hidden in plain sight,
yeah.
Right? Yeah.
Yeah. You should bring that up to Mallory. I'm sure she would.
It's a good one.
Be convinced.
my guitar slowly. What is it?
Gently weeps.
Gently weeps. I was in Phoenix over the weekend, walking around Scottsdale actually, and one of the stores had music playing, and it was Owl City.
Mm-hmm.
And the lyric was, "I'd like to make myself believe the earth turns slowly."
Oh yeah. Yep. Fireflies. Yep. Oh, okay. CD McCullers tagged me and said, okay, he's referring to the question that was asked of Desert File about when did the expansion of the universe slow enough to form planets?
Oh yeah.
That, I hate to say it. I keep saying this, but that's really just not my field. Cosmology is not my thing. And I really don't know that much about it. If anyone has questions about quantum optics, I'm happy to answer.
The quantum optics are actually, that's pretty interesting. So if you saw when I had the debate with Alan from Space Audits, he did he referenced a few experiments that people had done, and one of them was really interesting, where these different experiments with interferometers. So if you put a interferometer that has an area inside of it, a circle, triangle, square, rectangle, and you move it, you get the Sagnac effect.
Right.
And you can do it in a fiber optic, or you can do it in air, just with mirrors. So what if you have the emitter stationary, hitting a mirror that's on a moving platform, and then it bounces between mirrors on the moving platform, and then gets recombined onto the moving platform? Will that create a fringe shift? Then, and say these people did a series of different tests where they had the emitter on, they had it bounce till it's off, they had the emitter on, bouncing around and then recombining off the circle. They had where it would go and it would bounce, it would split, it would bounce, then it would in two paths, and then both paths would bounce down, reflect down to the moving table, move there, and then get recombined. A whole bunch of different combinations of that.
Interesting. The moving mirror it depends on exactly the way it's set up. You'll get to answer one question, you'll get a fringe pattern anytime that you have two possible paths that are combined at a beam splitter, and they have a well-defined phase between them. So that's when you get the interference fringes. That's why you don't get interference much with white light, is because the phases are all over the place. So as long as there's two paths that can be recombined, you'll get a fringe pattern. The effect of the moving mirrors will, my two immediate thoughts are, it'll probably cause a phase shift in at least one of the paths. That's kind of how a Michelson interferometer is set up. You have one of the mirrors moving back and forth. Or what I'm thinking of, actually, I'm sorry, is like what's called Fourier transform infrared spectroscopy, which is a Michelson interferometer with one moving mirror, and that introduces a phase shift. So that's one thing that the moving mirrors might cause. Another thing they might cause, although I'd have to noodle on this a little bit, is it might cause what's called radiation pressure. If the mirror is moving towards the light incident on the mirror would be blue shifted, and if they're moving away, it would tend to be red shifted in some way. I would have to kind of look at the scheme and noodle that a little bit, but that's my first instinct.
Well, I'll find that paper and get it to you so you can at least look at that. So what specifically types of things do you do in quantum optics?
Up to now, I can actually answer a question by Real Cygnus, who asks, so I'm doing experimental or theoretical. Up to now, I have been a theorist. My current PI advisor, or whatever, is a experimentalist. So I'm kind of pivoting to the experimental side. But theory is truthfully kind of where my heart lies. One thing I'm really interested in is like nonlinear optics, which is things where like photon number is not conserved. So you send two photons into the special nonlinear crystal and they combine to form a new photon at the sum of the original photon's energies. That's called, of course, sum frequency generation. And the opposite process of that is called parametric down conversion, which is you send one photon in and it splits into two in a way that conserves the energy. One thing I'm kind of looking at is that in a way that conserves the energy, quote, is there's a little bit of subtlety there, where the profile in frequency is actually is not a sharp delta peak at one frequency. It has the superposition of frequencies. So it's a Gaussian. And so there's kind of interesting things you can do with that. That's something I've been investigating a little bit. And there's a kind of my pet topic is something called like weak values and super oscillations, which is, suppose you have a beam of light or a photon, what have you, that can be in multiple different energy states. There's a way that if you combine those energy states correctly in this kind of quantum superposition, you can actually create a region of the wave function that looks like it has a higher frequency than any of those frequencies that it could have been, which actually raises really interesting questions about like conservation of energy. There's a paper, a name drop a paper by a guy by the name of Kir Aharonov. And the paper is called On Conservation Laws in Quantum Mechanics, where he discusses this effect of super oscillations. And that is kind of a pet topic of mine, something I hope to do a little bit of experimental work in.
All right, I've got a question from Coffee Breath. Says, you know why I love the neutron bar?
Why?
Because there's no charge.
Nice. Very nice. Nice dad joke.
Yep.
Let me see.
Well, I think that Desert File is wants to ask questions. So I'll give him a little bit. Otherwise,
I can hang around. Definitely.
And we'll wrap it. We did start a little late, but it's still good to end. When we're done here. So
yeah. So Desert File is going to come in a second.
I'm getting the idea that he has some questions.
Okay, cool. I'll hang around for a few more minutes at least.
Hopefully it's not too long. I would love to have Desert File on just to talk smart.
Yeah,
at some
definitely.
point. Maybe he wants to do a Toon Show chat at some point.
C.D. McCullough asks another question. He says, any thoughts on current teleportation or quantum entanglement research? Medial and denier say even an explanation of light slowing through glass would be a nice change with slowing in quotation marks. I'm not super up to date on like the Bell tests. I am kind of familiar with the historical Bell tests and all the different loopholes and whatnot. Sabina Hassenfelter comes to mind, who prefers my kind of personal least favorite loophole of superdeterminism. And that's kind of the only loophole that you can't really completely rule out. One interpretation of quantum mechanics I really like is called the transactional interpretation. And it's explicitly retrocausal. So wave function has a forward in time and a backward in time traveling component. And this is popularized by the physicist, it was created by the physicist John Kramer and popularized in the modern day by a physicist by the name of Ruth Kastner, who also dabbles mostly in philosophy nowadays, I think. But the transactional interpretation actually answers this question of like spooky action at a distance by saying when Alice takes a measurement at this space-like separated point, the effect of that measurement actually propagates backward in time to the preparation where both the particles were spatially together, and then forward in time again at the speed of light to Bob, and so that kind of resolves that spooky action thing. It's a really interesting idea. Aharonov deals in those kind of retrocausal interpretations as well.
It reminds me of my my explanation for what flat earthers would have to propose, or one of the things they would need to propose for cold moonlight. Because photons carry energy. They don't carry negative energy, right? So it could not make something colder. Now, of course, there's lasers that can freeze things. That's a whole different process than just light hitting something and making it warmer, or their claim, light hitting something and making it colder. In order for that to happen, the wavelength would need to be not, the longer the wavelength, the colder it is, the shorter, the hotter it is, right? So you get that wavelength longer and longer, you get to zero, and then you make it negative. Well, now with a negative wavelength, you can make it be cold, but a negative wavelength means that it's traveling backward in time.
Right.
So that photon hits the surface of something, travels back in time, and then hits the moon where it came from, and then is absorbed into the moon and makes it warmer.
Right, exactly. So it's the time reverse process. It's indistinguishable from a photon leaving the Earth and going to the moon, forward in time, as opposed to it's an interesting little subtlety there. A Coffee Breath says, what is a space-like separated event? It's just two space-like separated events refer to things that are separated in space, except space-like has a slightly subtle meaning in relativity. And you use that term when you're trying to refer to things that where the speed of light comes into play, where you can't have a signal travel between two space-like separated points faster than the speed of light. So that's all it means.
There's a good book that goes into that. And it's by who's the British Neil deGrasse Tyson?
Brian
Cox.
Yeah, Brian Cox.
He wrote it with someone else. Let's see. Why does E equals mc squared, and why should we care? So that book goes over why, and it gets into relativity, and it gets into the speed of light, and it talks about these angles that the things could go at, and that it's limiting to the possibility, so it leaves it in two possible 1/8 segments of this the angles possible. Anyway, the point is that mass, when you have mass, it takes some of the energy. It's as mass. I don't know.
Mhm.
It's not, my explanation is not nearly as good, and I haven't listened to it today. So I'm not.
That's interesting.
It's a great book. It goes over that. Obviously, I didn't quite get the description well enough to present it to you. Coffee Breath says, "Why can't dark matter be tachyons?"
Why can't dark matter be tachyons? I guess that would be kind of something you need positive evidence.
Explain tachyons first.
So a tachyon is a hypothetical particle. It is not measured or observed yet, at least, that in principle travels faster than light. And therefore, by the rules of relativity, some hand-wavy way, it travels backward in time. I don't really see a connection why dark matter would be explained in that way, but maybe I'm just missing some idea. But it doesn't seem super plausible on its face.
I think he's bringing up tachyons because the photons from the moon go backwards in time like tachyons do. So.
Oh, I see. Yeah, I encourage anyone interested in this whole backward in time thing to look into the work of the whole group of Yakira Haranov is kind of the leader of the group, and his proteges are Eli, it's technically pronounced Eli, it's an Israeli name, Eli Cohen, Cohen, and Avshalom Elitzer, Avshalom Elitzer. They have done a lot of really high quality work on the physics of can you interpret quantum mechanics in terms of like a wave function having a forward and a backward in time component. And of course, as I said, Ruth Cass has several books on the transactional interpretation, which is very similar to what the Haranov, Cohen, and Elitzer group promote, but not identical. Okay. So anyone interested in that should definitely check those authors out.
All right. Well, I am not seeing anything from Desert File. So what I'll do is I will contact him. I'll try to get him to come on.
Okay, cool.
At some point. Maybe you and he could talk, but I think what we'll do is we'll wrap this up here.
Sounds good.
And this I'll let you know when the it goes out. It'll be a while, but when I get enough episodes together to put out one per week for several weeks, I'll let you know. And people, you can go sub to the Toon Show YouTube channel to see it there, or you'll find them on the regular podcast platforms. So, Cody, cool. Thank you very much. This has been
thank you.
Great to hear, and we'll talk to you later.
Yeah, sounds good. Have a good one. Bye.
Here we go.
MC Toon, drop that beat.
All right, let it flow. Let yourself go. So I know that is the tempo.
So, yeah, let's do this.
Let's do this. Yo, it's MC Toon, the debunking tycoon. I shatter flat earthers, make them face the moon. Your attempts are decent, but they'll swoon in the face of my logic like a deflated balloon.
Oh, MC Toon, the monsoon of cartoons. I'm the real sage, send it first to their views. Your theories are like old brews, sweeping ignorance, or just spreading the views.
FDFE stands for fumbling the facts, evidently. I drop truth bombs so splendidly. Your approach is soft, mine's unrelenting. I bring the science while you're just venting.
MC Toon, the flipping with silver spoons. I have the pseudoscience to make them change their tune. You're the sidekick, I'm the room. When it comes to debunking, I'm the room.
Dizzle. In the rizzle dizzle.
But hey, FTFE, we share the creed to educate and debunk, plant the seed. Though in this rap, it's clear indeed I've got the upper hand in word and deed.
All right, hold on a second. The Zoom call died. Everything died. No.